Now see here basic transistor configuration and transistor characteristics. So, we have seen transistor has got the 3 terminals and each terminals, one is known as emitter, that is, and another is base, another is collector, that is represented by C. And now we have seen the circuit diagram for the working of the transistor. Base was common to both the sides, N side, that is the input side and output side. So, we can make any one of thing is common to the both the sides, and according to that configuration of the transistor is decided. So, first we can take as a common base. So, common base configuration means here the base is common. Second one is common emitter. Here emitter is common to the both the sides, input and output, and third one is common collector. Here collector is common to both the input and output side. But now see here, common collector is not used. Most widely used configuration is the common emitter configuration. So, we will study in this chapter only the common emitter configuration here and the working of the transistor as common emitter configuration. And we will be using common emitter configuration further like a transistor as a switch, transistor as an oscillator and transistor as an amplifier. So, now let us see first the characteristics of the transistor for the common emitter. Suppose I have taken first NPN transistor. NPN transistor is like this. Here, this is here emitter, this is here inside here the circle I have placed, this is grounded both the side, it is done here the common. Now, there is a resistance that is RB, and now here a battery is connected, and battery is such that this is called VBB. Input side is in the forward bias. Because this is emitter, this is base and this is collector. So, base is connected to the positive terminal of the battery. So, the input region is here in the forward bias. Now, see here there is a collector side here, there is a resistance RC, and here this is NP and this is negative, it has to be kept in reverse bias. So, it has to be connected with the positive like this, and this is here, it is called VCC. Now, see here in this circuit, this is here IE, here you will be getting IB and here you will be getting here IC. IC is measured in milliampere, IE is measured in milliampere and IB is measured in microampere. And now, there is a base and emitter, there is a voltage that is called VBE, and now there is also the voltage that is called VCE, that is collector and emitter. Now, in the first case we study here, when the VC is increased and it is sufficiently kept larger to keep it is in the reverse bias. So, first for the input characteristics, when we take here input characteristics, see here in input characteristics what is done here, the graph is drawn between the IB and VBE. This is the base current and base emitter voltage, keeping VCE constant, but VC is kept constant at the large value, so that the properly reverse biasing is done here. And also see here when the VCE increased, potential drop also here at the VC and B, VCB, but there is not much change in the IB because of the increase in the VCE. The graph obtained for this is something like that. Here we get IB and here we get VBE, and the graph is something like this. So, up to the certain voltage here it is not giving any current, but as this forward biasing is increased much, the graph is obtained, there is a significant increase in the base current, but this base current is measured in microampere. So, now this was the input characteristics. Let us see output characteristics. So, now we will see here output characteristics. So, see here in output characteristics actually we draw VI graph between IC and VCE by keeping IB constant here. So, if you keep IB constant and keep on changing IC, VCE and you measure the value of IC, you will be getting the graph is something like that. Here that is VCE and there is IC, graph is here like this and then it becomes constant here in this manner. Suppose if you have placed here IB is equal to 10 microampere, IB is equal to 20 microampere and like this you can keep on increasing. You will see here there is a slight increase here in IC, but when IB is 0, IC is also 0. As you increase IC, IB here, there is an increase linearly, then it becomes almost constant. If you increase IB slightly, again there is a small increase in this, and there again the current will become IC constant. So, this is the graph for here the output characteristics. So, this can be said output characteristics, and now we can calculate input resistance and output resistance also. So, when we calculate here the input resistance and output resistance, so we can write input resistance, that is Ri is equal to delta VBE upon delta IB, and keeping here VCE constant. So, we can calculate this. Our output resistance can be calculated VCE upon delta IC and keeping here IB constant. And also we have seen whenever there is an increase in the IC or input biasing, there is a like a forward biasing is supposed to increase, there is increase in IC, as a result there is increase in input current, that is IB also. So, we can define one quantity that is called amplification factor. Amplification factor, that is represented by beta. Beta can be written here delta IC upon delta IB. For this is beta AC. But when you are writing here beta DC, that can be written here IC upon IB. But we know it IC is greater than IB. So, here the beta is greater than 1. Because of this here property, here also the transistor can be used as an amplifier, but when the transistor is used as an amplifier, it is used in active region.